until this point, we've described a way of programming that, frankly, is pretty close to programs we could have written in plain old C. Yeah, we've seen several C++ specific features that make things better, like streaming and strings and vectors and exceptions. But the basic style of programming is one that we could have been doing in C. And that style is called procedural programming. It relies on functions, also called procedures, to organize the computation. Now, I started with a procedural style of programming since I think it's easier to learn and understand, and it still forms the basis for a lot of the other ways that we'll write code. We'll still need everything that we used for procedural programming. But now we're ready, in the next 6 lectures, to learn one of the key advances in C++, and that's object-oriented programming, sometimes abbreviated OOP. Now, there were pure object-oriented languages before C++, and there have been languages developed after C++, like Java, that go all out for object-oriented programming. It's the only way to program in those languages. By contrast, C++ lets you use both a procedural and an object-oriented style. And compared to other languages that offer some of both, like Python, C++ has a very complete set of object-oriented features. It enables you to program in a strict object-oriented style if you want to. When we use object-oriented programming, our development is centered around the creation of what are known as classes. Classes present an overall way of organizing the computations in a program, where objects are just particular instances of classes. The concept of classes is important enough that when C++ was first being developed, it was originally called C with classes. In this lecture, I want to start with the feature of classes that I think is the most useful part of object-oriented programming. It's called encapsulation. For illustration, imagine that we want to write a program where we're keeping track of vending machines. The sort of machine where you put in money and press a button to get a snack or a soft drink or whatever's being sold. We want to be able to track what happens with a vending machine. Money taken in, the number of items left inside, maybe when it's time to reorder, and so forth. Our focus in object-oriented programming is to identify objects. In the case of vending machines, any particular vending machine is an object. For example, the soda machine that's sitting in the lobby of my building is an object. It's a single, specific, actual vending machine. But we would also like our program to handle vending machines more generally. So, we could also have a vending machine class, a way of referring to all vending machines. An object is just one particular instance of a more general class. For a given class, we can have lots of actual objects. In addition to the soda machine in the lobby, we might have a soft drink machine in the break room, and a snack machine in the lobby, and so forth. When writing code, we can think of each class as referring to a new type, a type that's defined by the programmer. So, when we define the class vending machine, we're defining a new type of variable. Then we can use that new type to define any specific machine. Defining each specific machine looks like how we defined a variable. That is, defining an object of a class is just like defining a variable of a type. In fact, that's how we'll use these things. We'll define a class like vending machine, and then we can declare variables of that type. We can write things like vending machine, lobby soda machine. Now, although each vending machine object gets declared in a way that makes it look like a single variable, in reality, each vending machine contains more variables. For instance, there are variables for money. We might want to know how much money someone has put into the machine so far toward buying something, the credit that they've accumulated. We might want to know the current total amount of money collected by the machine. We might need to keep track of the prices for all of the items. And we might want to keep track of the inventory level of each item. In addition to the data that we want to track for the vending machine, we also have actions that we want a vending machine to be able to perform, also known as operations. And these actions might include taking in money, or giving the customer an item, and returning change. And maybe we also want the vending machine to be able to report inventory levels so that it can be refilled to the proper amount. Now, how do we keep track of the data? With variables. And how do we handle the actions? You know this, with functions. Okay, so variables and functions sound familiar, right? Well, what's cool about object-oriented programming is that we can put all of these variables and functions together in one package. We can collect all the stuff related to a vending machine, all its data variables, and all the functions that it needs into one vending machine class. And we don't need to let someone outside the vending machine know about everything going on inside. The inventory data, for instance, could be hidden. Because all that data and all those functions are wrapped up together in one package, it's a process we call encapsulation. By the way, 3 classes that we've already been using are vector, string, and fstream. And these were predefined classes that we accessed from the vector library, the string library, or the fstream library, using #include. For example, in a string named s, if we wanted to get the length of the string, we would write the string name, followed by a dot, followed by length parentheses. And that gets the length of that particular string. What the string class is doing is making use of an encapsulated function, where the string variable s is really a string object. In s.length, length was a function that belonged to the particular object s. So, let's see how we can create our own class using the vending machine example. To keep things simple, we'll start with a vending machine that only has one product. We declare a class similar to how we declare a function. It'll typically be defined outside of the main function, closer to the top of the program. We start with the keyword class. Then we give the name of the class. So we'll call our class vending machine. The name of the class will be the name for the new type we create. Next, we have curly braces, which are here to group the definition of the class all together. At the end of the curly braces, after the curly braces, will be a semicolon. Whoa! Now that semicolon is tricky. It's one of the few times that we need to add a semicolon after curly braces. Remember, classes need semicolons. Fortunately, if you forget, the compiler will catch a missing semicolon and remind you to put it there in most cases. Now, once we've got a class, we can declare objects as instances of the class, just like we would any other variable. So, here's our example. In this case, we've declared a class named vending machine by writing class vending machine curly braces semicolon. Now, obviously, there's nothing in the class at this time. So far, it's useless. But this gives us the ability to declare objects of type vending machine. Remember, a class is a way of defining a new type. So classes are defined outside the main or any other function. Objects can then be declared to be of that new type. Variables are typically declared inside of functions, including main. Now, because a class is a type, and each object is declared with that type, an object is like a variable of that class type. So, an object is like a variable, just an instance of the class that defines it. Now notice how we declare our 2 vending machines. The first one is called lobby machine, and the other one is called break room machine. All we do to declare them as variables is write vending machine lobby machine and vending machine break room machine. And these commands will create 2 vending machine objects. Okay, now let's look at how we can store data in the vending machine class. A class is going to contain inside of itself a set of variables and functions that we call member variables and member functions. The class is a way of grouping all those member variables and member functions together, encapsulating them. So, when we create a new object of that class type, we're also creating a bunch of subordinate member variables defined by that class, but with values specific to each object. Basically, those subvariables belong to the object as its member variables. For vending machines, one of the things that we wanted to store is the price of the item that the machine sells. So, inside of the class definition, we'll create a floating point member variable named price. Now, before we declare the member variable, we put the line public colon. And this just means that the member variable can be seen outside the class. We just declare this similar to the way that we would declare any other variable. The type, the name of the member variable, then a semicolon. In this case, that's float, price, semicolon. And that means that a vending machine contains a member variable, sometimes called an attribute, named price. Every object of type vending machine will have this subvariable inside of it, named price. To access this member variable, the attribute subvariable that's included inside of an instance of the vending machine class, we just use the object name followed by a period, followed by the variable. So, let's see a specific example. Remember, we've defined a class, vending machine, and the class is a member variable or attribute named price. So, if we've declared an instance of a vending machine, like the variable lobby machine, we say this is a vending machine object. To access the price member variable inside of the lobby machine, we write lobbymachine.price. Let's step through this program line by line just to make sure it's clear what's going on. We have our class definition at the beginning. This declares a vending machine type that's available to the entire program. In this case, the class contains just one public member variable, a float variable named price. Now, when we execute the first line of the code in main, it'll create a new object named lobby machine. That will be an instance of the class vending machine. That instance will contain its own member variable inside named price. The next line will create another new object named break room machine. Again, it'll be an instance of the class vending machine, meaning that it will have its own variable inside named price. Then, we'll assign a price of $1 to the lobby machine. We write lobbymachine.price, and this means that we're referring to the variable price within the object lobby machine. We assign that the value 1. And so the memory will store 1 in that variable in that object. Likewise, when we assign a price of $2.25 to the break room machine, that will assign the value to the price variable in that object. Now notice that the price is not shared between the two instances of vending machine. Each instance, each object gets its own price variable. So, in the end, when we print out lobbymachine.price and breakroommachine.price, we're printing out the values from two different variables. Now we can, of course, define more than one member variable within a class. So let's create a new member variable for credit, and another for money collected, and an integer variable for inventory. We can then give any object access to each of the member variables by writing .price, .inventory, .credit, and .money collected. And this works just the way that accessing the price did. We're accessing a variable that's an attribute or member of the specific object. Now this idea of packaging data together in one larger container actually goes back to the days of C. Back then, the container was called a struct, short for structure. Well, structs are still allowed in C++, but they're now almost the same as classes. The use of struct and class are pretty much interchangeable. The thing that really distinguishes the C++ class from the old-style struct is the ability to have member functions. Another term that you may encounter for member functions is to call them methods of the class. So, methods are the same as member functions, just as attributes are the same as member variables. Member functions get declared just like member variables in the class definition. Then, to call the function, we give the name of the object, then a period, then the function name, along with the parentheses and any parameters. Let's try a really basic example. Suppose we wanted to make our vending machine more friendly. Here we have defined a function called printHello that will just output the word hello. And we define the function within the class definition, so it's a member function. Then, in the main program, we have an instance of that class. In this case, the class was a vending machine, and the instance is named lobby machine. So we can write lobby machine dot print hello parentheses. And when this is run, hello is indeed printed to the screen. Okay, that's a way to print a message to the customer. Now suppose we want the machine to be able to tell workers how many items are remaining inside, so that we know if it's time to restock. So let's create a function named numberRemaining that will return to us the number of items remaining. Now, does this function need any parameters? No. We're just going to return an integer, the number of items in the machine. So the function will be declared as int numberRemaining parentheses. No parameters needed inside. Now, the body of this function is going to be really simple. It's just going to be return inventory. Notice that since the function and the variable are part of the same class, the function can refer to the variable simply as inventory. There's no something dot inventory needed. When the function that's part of the class refers to inventory, it will use the value in the inventory variable for whichever object that it's a part of. So, in this case, when we set the inventory level to 250 in the lobby machine, then calling lobby machine's member function numberRemaining will return the value in that lobby machine, 250. Okay, now let's look at how our vending machine will handle money. First, we need to be able to take in money. When someone puts money into the machine, they should have a credit for that amount of money. So let's see what that member function would look like. We'll call the function depositMoney, since it will let money be deposited. The depositMoney function will again be very simple. It doesn't need to return anything, it's just a deposit. So we declare it as void depositMoney. And the function will take in a floating point number, the amount of money that's being deposited. So we have open parenthesis, float, amount, close parenthesis. Whatever money is deposited will go toward a credit in the machine. So the body of the function will just increase credit by the amount of the deposit. Credit plus equals amount. That's all it needs to do. We'll also add an output statement to note what the current credit is after the deposit is made. Then in our main program, we can create a vending machine object and set the credit in the object to 0. Then we'll deposit 25 cents, 25 cents, and 10 cents. If we look at the credit at this point, it's 60 cents, just like we'd expect. Now, it's not good practice to declare variables without initializing them to something. We don't want to accidentally access a variable sitting around with who knows what data inside. To initialize the member variables, we just write an assignment operation at the time of declaration, just like with any other variable declaration. In the code here, we set both the credit and money collected to 0, a default value of $1 for the price, and an inventory level of 0. To return the change from the machine, we could write a return change function. It would take whatever credit is currently in the machine, return it, and set the current credit to 0. And we output the amount of money that we're returning. Now, let's create a function for pulling together the specific steps that a vending machine goes through when the vending machine is asked to vend an item. For an item to be vended, there needs to be an item in the machine, and there needs to be enough credit to purchase it. And if there is, then we'll distribute that item, we'll deduct the price from the credit, and then we'll return any change. Now, pause and try writing this routine yourself. Make it a function that returns a Boolean, true if an item is vended, and false otherwise. Okay, let's look at pseudocode for the steps that this vending machine program will follow. First, define a function in the class named vend that returns a Boolean. Check to see if there's enough credit to purchase an item. Check to see if we actually have any items in inventory. Handle the transaction, adjusting credit, money collected, and inventory. And return any change to the customer. Now, pause and use that to see what you think the code would look like. Okay, here's how a vend function might look. We'll define a function in the class named vend that returns a Boolean. We'll first check to see if there's enough credit to purchase an item. If the credit built up is less than the price, we'll return false. Nothing will be vended. We'll also print out a note that more money is needed. Next, we'll check to see if we actually have any items in inventory. If we're sold out of the product, that is, if the inventory level is not positive, then we print a message to that effect and we return false. Now, if we have sufficient credit and there's inventory, then we vend the item. There are several things that we need to do. We need to deduct the price from the current credit. Credit minus equals price. We can then increase the amount of money collected plus equals price. We'll output that we're vending an item and reduce the inventory level by 1, inventory minus minus. Then we'll return any change to the customer, calling the return change member function. And finally, we return true. If we run this program, we see what we would expect to from the process. As we add money in, the credit increases. When we vend an item, we get that notice and we get some change back. And if we were to look at the variables in the lobby machine object, we'd see that the inventory had been reduced and we had some money collected. So, that's how member variables and member functions can be defined. Now, so far, we've always had public colon at the top of our class definition, meaning that everything we declared after that in the class is a public variable or public function, available for anyone to call from anywhere. But we can also have private variables and functions, which we get by writing private colon beforehand. When a variable or a function is private, it's accessible only to other parts within that class. That is, the functions within that same class can access the private variables and call private functions, but those outside the class cannot. So first, let's see how it works to make something private. Going back to the vending machine example, we've now marked the member variables as private by writing private colon in front of their declarations. The member functions are still public. We've written public colon in front of them. Now, when we try to run this code, we get an error coming from the line in the main program where we try to access inventory to assign some initial inventory to the lobby machine. This is not allowed. Since inventory is private, we can't access it from outside the class. So to fix this, we can move the public colon line up above the inventory member variable. And that will make inventory public, meaning that it's okay to access it. And now if we run the code, everything's fine. We're able to access inventory from outside the class, so the line that gave us trouble earlier is no longer an issue. Now, notice that we did not get a compiler error inside any of the many places inside our member functions where we accessed member variables. Because we were accessing the private members from within the class, everything was okay. Only when we tried to access those members from the main function was there an issue. Now, the public and private designations can be used multiple times in a class definition. However, it's common practice to put the private members first and the public members after that. And it's also common practice to put all the member variables first and the member functions after that. Attributes first, then methods, to use the other terminology I mentioned. Besides public and private, there's also protected, but for the cases we've seen, protected acts just like private. And we'll look at how they differ when we discuss inheritance in Lecture 19. In a class definition, the default assumption is that the members are being defined as private. That's why we had to have public colon at the beginning of our examples. If we'd left it off, then everything would have been seen as private. Now this is actually the main place where there's a difference between the C++ class and the C++ struct. The code that you see here illustrates two equivalent formulations. In a C++ class, the default is that everything is private, so we had to declare public colon. But in a struct, the default is that everything is public. Why the change? I mean, why make private the default? In fact, why would we ever want anything to be private? Doesn't that just make it more difficult to access things? Well, it does, and actually that's the point. When we're thinking about developing a class, we want to think about what that class is actually needing to do. Now remember how when we first talked about functions, we talked about making things conceptually simpler. We had functions that we could treat like a black box. We know what goes in and what comes out, and we don't need to worry about the inner workings. Well, classes use the same idea but taken up a notch. When we design a class, we want that class to provide self-contained data and functionality to those using it. In our vending machine example, we want to provide the ability for someone to deposit money, to get change, and to vend an item. But the user of a vending machine really shouldn't be worried about what the internal values being stored are, or how everything works underneath. The term we use for this is information hiding. We're going to hide information from those outside the class by keeping it private inside the class. And this helps us make sure that nothing outside the class can mess up stuff inside the class. In our vending machine example, we only want to increase the money collected when we actually sold an item. So for that to be consistent, we only want our own vend function to be able to modify the money collected. It would open us up to all sorts of problems if someone using the vending machine could just change the amount of money it thought it had collected. The data would then be inconsistent. Instead, by hiding that information so that only the class's own member functions can have access to it, the class can ensure that it maintains consistency. Now, it's not uncommon for all of the member variables to be private or protected. And that makes sure that nothing outside will mess around with the internal structure of the class, unless it does so through one of the approved channels, one of the public functions. But it's still common to need to adjust those variables or find out what they are. So, in our vending machine, we had a routine, number remaining, that would tell us the inventory level. And this type of routine, that basically just returns the value of some private member variable, is called an accessor function. Accessor functions let you read information from the class. And basically, they provide one of those approved channels by which information is allowed to leave the class. Now, there are also what are known as mutator functions. A mutator function will let you modify the value of a private member variable. For instance, let's say that in our vending machine case, we wanted to let someone open up the machine to restock the inventory to a certain level. In this case, we wrote a restock function that takes in an integer and sets the inventory to that level. For example, if we want to fill the machine to 100 items, we would call restock with an argument of 100. restock is a mutator function, since it just modifies one of the member variables. Now, down in the main function, when we have a vending machine object, even though inventory is a private variable, we can use the mutator to set the inventory level. We just call restock with the argument of the level that we want. And we can use the accessor to find out the inventory level at 2 different points in the program. So, you might be wondering, if we're going to have accessor functions to read the value of a private member variable, and we're going to have mutator functions to modify the value of a private member variable, why not just make the member variable public? Well, the reason is that we still control access to the member variable through the accessor or mutator. That is, we can limit what values those functions can take, and what something outside the class is allowed to see or do. In the mutator we just had, for instance, we could put in a check to make sure that the new inventory level was not a negative number, since a negative number would be meaningless for inventory. If the inventory level was a public variable, we would have no way to stop something outside from just redefining the inventory level to any value, including a negative one. Or we could log every time a variable is accessed by the mutator. And when debugging, accessor and mutator functions give us a line of code that we can set a breakpoint at, so we know when a member is being accessed. Conversely, we have no way of automatically pausing when a public member is being changed. So, accessors and mutators help us ensure that the overall object maintains internal consistency whenever it's used. Object-oriented programming is now probably the dominant programming paradigm, and it's also fundamental to making full use of the power of C++. I personally remember programming in C before C++ was widely known, and using lots of hacks and workarounds to try to get something like the encapsulation that's provided so nicely in C++. Now that we have classes, we're able to talk about each class in the same way that we talk about string, int, float, and boolean types that we've been using so far. So get ready. The number of types is about to explode from just a handful to whatever you can imagine. Each class that we define becomes, in effect, a new type. Our vending machine class all by itself is a new variable type. Encapsulating variables and functions into a single class lets all the parts work together as a whole. We have information hiding so that we can keep stuff more consistent and orderly internally, while also gaining more control over external interfacing. In the next lecture, we're going to be discussing how to set up classes and operations on classes any way we want, so that our setup makes the most sense for the program at hand. I'll see you then.